Our project is CLEAR, sponsored by VoltServer, which stands for Colored LED Event Automated Reader. Our technical directors are Camille Gerardo and Stanley Mylinik. Our team is comprised of 3 designers, 2 being electrical engineers, myself and James Kai, along with 1 computer engineer, Aram Elmayan. VoltServer is a company based in East Greenwich, Rhode Island, most known for developing and distributing a platform called Digital Electricity, which is a safe and innovative power distribution platform. The goal of our project is to develop a mountable LED sensor system to be able to visually analyze RGB status LEDs and blink sequences incorporated in VoltServer products. This will eliminate the need for VoltServer technicians to manually verify and decipher these signals. This product would allow VoltServer technicians to save time and thereby be more productive, saving company time and money by automating this process. In order to meet our ABO, we would need to develop a prototype 1.5 by 1.5 mountable PCB that would be able to be used on any VoltServer device. Along with this, development of a sensor system that would be able to read status LEDs and blinking sequences to decipher them to the users necessary as well. To achieve our ABO, we would need to provide all schematics, layout, fabrication, assembly files for the PCB, along with firmware and software source code. We would also need to provide a complete bill of materials along with a detailed system user manual. Currently, our key accomplishments include component research and selection, LED sensor testing, and PCB design, along with sensor algorithm and sensor data testing and collection under different lighting conditions. Below is a block diagram of how the overall product will function. I will mainly be discussing LED sensor algorithm along with components. This is a list of my key technical accomplishments within the fall semester, where I was able to create a LED sensor algorithm flowchart along with component research and selection, and I was also able to redesign the LED sensor array and multiplexer schematics. Our flowchart is made to aid in the visual understanding of the preliminary design of our sensor algorithm, where after turning on the device, it would need to verify ambient light. Then it would have to be able to calculate what RGB color is present. Afterwards, it would then calculate the length of the signal and relay this to status LED code to the user. The part we selected was the same one as last year's design, the APS 5130 PD73P22 RGB color sensor. It's a 4-pin component that has 3 RGB signal outputs. For our design, we're going to be utilizing a 3x4 array of these photodiodes, meaning that there would be 12 photodiodes in total. That means there would be 36 RGB signals present that would have to be relayed to the multiplexer. The multiplexer that we decided to use was the CD74HC4067. It's a 24-pin component, and our design will use 12 of the 16 present signal inputs to account for the 12 signals per each color. 3 multiplexers will be utilized within our device for the RGB signals. My future technical accomplishments will include LED sensor testing, along with designing the PCB clear prototype, and I will also assist in the development of the sensing algorithm firmware. The next designer who will be speaking is computer engineer Aram Elmayan, who will be mainly discussing microcontroller research, sensor data testing, along with PCB test boards.
This is a list of my technical accomplishments that I made this semester. I was involved with researching parts and collecting sensor testing data, both of which were efforts shared by the whole team. I researched the PIC microcontroller that we'll be using, as well as took note of some important pinouts and functions. Lastly, I created 3 PCB designs, a breakout board for the multiplexer and voltage buffer each, as well as a test PCB for the sensors in a 4x3 array to facilitate firmware testing. Here are images of the breakout PCB designs. On the left is the analog device's voltage buffer we chose, and on the right is the Texas Instruments 16-input multiplexer. The via holes on the sides of both are small enough to solder a wire to, and they act as test points. The basis for these designs were to test the tiny chips on a breadboard before using them for our final prototype PCB. Another benefit is that it isolates the components and can narrow down errors to a specific component. I also created a test PCB for the 4x3 sensor array, as can be seen on the right side. On the left is the schematic for this PCB. The sensors receive a 5-volt input for power, and the marked voltage dividers bring half the voltage into the buffer in order for the microcontroller to be able to read it, as it can only decipher up to 3.3 volts. The goal for this PCB was to speed up firmware development by having a sensor array similar to the prototype PCB. This allows us to use the same code as in testing when programming the main PCB later on. Next, the microcontroller we're using is from the PIC family. It contains 80 total pins, 69 of which are input-output, and 24 of those have analog to digital converting capabilities. For the time being, though, we're going to use a development board until the prototype PCB is built. Some important pinouts that I found from my research include the programming pins, which are used to load the software into the microcontroller's memory, highlighted in green on the right side. The UART pins, which are used to communicate data between the chip and computer, highlighted in orange, and the clock pin, which is used to provide the microcontroller with a clock signal, highlighted in red. Also, at least 6 digital outputs and 3 analog to digital inputs will be necessary for our design. My future technical accomplishments include developing the GUI for board communication, developing firmware for the sensor algorithm, and working on the TX550 mounting solution. So now I'll pass it off to my teammate James.
Thank you, Aram, for the introduction. My first technical accomplishment this semester was redesigning the power system for our PCB. Next, we built a testing apparatus as a team, and I conducted 2 series of tests, recorded and charted the data. While Aram and Tom worked on the PCB design, I began making developments with the firmware by establishing serial communications with our development board and beginning the designs for our main state machine. Last year's team used DC to DC converters to power the PCB and microcontroller. However, they made a mistake on the complicated implementation of their chosen part that ultimately led to their board to fail at the end of the year. To avoid any similar problems, and since our PCB required a smaller size than last year, I decided to use 2 voltage regulators that required less external circuitry than the DC to DC converters, and they were simpler to implement. After finding one 5-volt and one 3.3 volt regulator from the LD2985BM family by ST Microelectronics, I used the datasheet to determine the external capacitors needed to safely operate the regulators. Next, we worked as a team to develop a testing apparatus for our photodiode-based RGB sensor. This consisted of a RGB sensor that was soldered to a PCB test board, which you can see on the bottom left of the slide. The sensor had 3 wires leading to a breadboard, 1 for power, and the other 3 for red, green, and blue photodiodes. The breadboard contained resistors of either 16.4 or 50 megaohms, and we used multimeters to measure the voltage drop over the resistors to calculate the current being generated by the photodiodes. Now, to implement the RGB LEDs, we used 6 half-inch wooden dowels to hold the cardboard over the sensor PCB at different heights. We cut a hole through the cardboard to easily change which color LED we could use for the tests. Here are the results for one part of our testing using the 16.4 megaohm resistors. I designed the following table to keep track of each different change made for the tests. The first column, labeled lighting, defines the lighting of the room the test was done in, since ambient light will affect the sensor readings. Next, we have the LED color being used, the height of the LED above the sensor, which color sensor is being measured, our resistance for the test considering the parallel 10 megaohm resistance of the multimeter, our measured voltage, and lastly the calculated current with Ohm's law. Next, I designed the chart on the right so that our team could easily visualize the data for all the tests I conducted. I graphed the change in current with respect to the change in distance, since the intensity of light heavily relies on the distance from the source. Finally, I began working on the firmware for our microprocessor while my teammates designed the PCB. I designed the state machine diagram on the left to visualize how the state machine is roughly going to operate. On initial startup, our state machine will move into the idle state and then check if it requires a calibration through a flag set up outside the main loop. It will perform an initial calibration and begin the test if one has been ordered. After a test, our machine will return to the idle state. When called upon for another test, it will take a reading of the ambient light in the room, and if it is outside an acceptable range of error, it will perform a recalibration before testing. In order to send and receive commands, we would be using serial communication through UART. I was able to set up reading and writing to the UART through PuTTY, which you can see from the screenshot of the terminal on the right. My future technical accomplishments are to complete the firmware with a fully developed algorithm, assist in developing a smaller mounting solution using the basis of last year's design, and to design a GUI for user interaction with our device. As a team, our key future accomplishments are to develop the accompanying firmware, redesign the mounting solution, finish the prototype of the PCB, develop a GUI, and create a user manual. Each team accomplishment has our overall confidence level of reaching its completion by next April right next to it. Nearing the end, we would like to graciously thank VoltServer for sponsoring our project and specifically our technical directors, Camilo Geraldo and Stanley Mielnek. Thank you, Camilo, for being an extremely valuable resource to us during this first semester. We would not be as successful without him, and thank you, Stanley, for taking the time out of your busy schedule to visit us and check out our progress. Finally, we would like to thank Consulting Director Mike Smith for all the assistance he has given our team in designing our PCB, and give a huge thank you to Dr. Sunak for all the time and dedication he has provided to the Capstone program. Without his hard work, none of this would be possible. Thank you from Team Clear.